Welcome to Electrostatics Part 4. Today we learn about electrostatic potential, what is the magnitude of electrostatic potential at a point, and what its physical meaning is. Here see the definition when we are going to electrostatic potential. Electric potential is a physical quantity which determines the flow of charges from one body to another. It is a physical quantity that determines the degree of electrification of a body. Electric potential at a point in the electric field is defined as the amount of work done in moving a positive charge, unit test charge, moved from infinity to a point inside the field or against the field without any acceleration. Means it is the amount of work done in bringing unit test charge, means here unit positive charge from infinity to a point inside the field. When we are doing work against the electrostatic field. That when we are moving this unit positive charge without acceleration, the movement should be without acceleration, means the motion should be purely against electrostatic force alone. Then only the calculated one is exactly gives its potential. If we are bringing charge Q, positive charge Q, then the work done is here stored in the form of electrostatic potential energy. The basic difference is in case of unit positive charge, electrostatic potential. If we are talking certain amount of positive charge, then it is electric potential energy at that point. Now next, if you see the formula, the work done to move from point A to B inside the electrostatic field, integral over E bar dot dl bar, the formula is in front of you. According to the definition, RA is infinity and RB is a certain distance from the source, let it is R. Then we have the expression V. See here we are in the expression we are moving Q naught charge. So if the total work is divided by this Q naught charge, we get the work done per unit charge. This is what the potential at a given point, and SI units are joule coulomb inverse, Newton meter coulomb inverse. Electric potential difference. What is electric potential difference? Inside the field at any 2 points, suppose we are having A and B, then the work done in moving the charge from A to B is integral over A to B E bar dot dl bar. Then we get the potential difference between these 2 points, VA and VB. So VB minus VA is the potential difference. So the potential difference between any 2 points is the work done per unit charge. Work done per unit charge. Now further, if you go, electric potential and potential difference are scalar quantities. These are two scalar quantities. Next, when we are talking about electric potential at infinity is 0. The electric potential near an isolated positive charge Q greater than 0 is positive, and that near an isolated negative charge Q less than 0 is negative. Here potential is a scalar quantity. Remember, still the potential here we are taking positive and negative in the sense work done by the system, work done on the system. So here CGS units are not more important for us. Now electric potential due to a single point charge, this derivation we will look out. If plus Q is the charge, electrostatic field is emitting radially outward, and we are taking a point or charge Q naught at any within the space region of electrostatic field, then it experiences a force Q naught E bar. When we are talking about the Q naught E bar and the distance from this positive charge to this point P, which is Q naught charge, when we are keeping the separation between them is say X. Now we are moving against the field. We have to move against the field, so we are moving P to Q, and finally we will moving by a small displacement dx. The work done against this force F is equal to Q naught E. The work done to move this one is Q naught E. Integrating to calculate the total work done, both sides, dw is equal to f bar dx bar. If we are integrating both sides, we get the net work done. So when we are talking about the calculation and then total work done, here the expression simply dw is equal to this one, and the final expression E is equal to Q by 4 pi epsilon naught x square. So the part, when we are talking about the integration part, if you are bringing this, simply the final expression for electrostatic potential at a point P at a distance r from the point source, so V is equal to Q by 4 pi epsilon naught r. Electric potential due to a group of point charges. So just like in case of electrostatic field, there we are using vector sum. Here simply the potential should be added algebraically. The net potential at a given point is sum of potentials due to group of charges acting. So potential V is inversely proportional to R, whereas the force and the field obey inverse square law, means inversely proportional to square of the distance. Potential is a scalar, whereas force and electrostatic field are vector quantities. Next we are going for electric potential due to electric dipole at a point on the axial line, at a point on the equatorial line, at a point anywhere. So the potential at any point due to a dipole. These are the three cases. Here axial, the case is very interesting. So the potential we are going to calculate point P. So this is the first expression. So the distances are measured from O to P. So the total distance is supposed 2L, the dipole length, and the separation from center to here, the measurement X is the point distance. So if we are talking about the negative charge, if you are talking about the positive charge, according to that we are having Q. Here in the case, from here to here is X, but we want this distance, this separation plus Q to P. So we have to subtract L. So that expression, that distance is nothing but X minus L. So similar negative charge. So here we are calculating from here to the point P, A to P. So the distance is X plus L. So the total distance here we substituted X plus L in the potential formula. The net potential Vp is equal to sum of the potential due to positive charge and negative charge. These two gives the net potential at the point. So the expression here we are having at a point on the equatorial line. This at a point on the equatorial line. In the previous case, how we calculate the same way. Here we are taking a point Q at y distance because it's represent y axis. In the previous case, it is axial line x axis. But here the distance is A to Q is this is the distance, B to Q is this is the distance. So these distances means if you consider this is a right triangle. In this right triangle, here the length L and this is y and this is the hypotenuse. By using the Pythagoras theorem, we can calculate the distance of AQ as well as BQ. So this is one method, and here if you observe, this is the perpendicular bisector. The perpendicular bisector, any point on the perpendicular bisector of line joining two points are equidistant. So here, as earlier we discussed, plus Q charge, the work done here the potential is positive, minus Q charge, the potential is negative. So here distances are same, magnitude is remain same, hence the net potential is 0. When we are adding these two, what is happening? This is 0. So now the logic what we learned is simply understood, I think. Next part is equipotential surfaces. Means those points which lie on a surface having the same potential. Those are called equipotential surfaces. So a surface at every point of which the potential due to charge distribution is same is called equipotential surface. For uniform electric field, so this is the equipotential surface, this is the equipotential surface, and this is the equipotential surface. But the field is gradually decreasing when we are moving away. It means the potential at this point and the potential on this surface are not equal. Okay. So next, here plane of equipotential surfaces. So this is the point source. The equipotential surface in case of uniform electric field, planar sheets. In case of point source, spherical symmetry. This is the equipotential surface here. So now these are the surfaces, and the work done between any 2 points. If suppose you want to move a point charge group, any magnitude charge between any 2 points on an equipotential surface is 0 work done. Why? Because those 2 points have the same potential. So the work done, the work difference between those 2 points is 0. So if you move a charge along the equipotential surface, the work done is 0. So these are the few properties here. The few properties when we are talking about the first one is the work done is 0 when we are moving, and the WAB. The second one is the electric field is always perpendicular to the element of the equipotential surface. Since no work is done on an equipotential surface, the E bar dot dl bar is 0. That is, E dl cos theta is equal to 0, cos theta is equal to 0 when theta is equal to 90 degrees. So these are the few properties of equipotential surface. Next, when we are talking about your equipotential surface, they indicate stronger and weak electric fields. How they indicate? The electric field is defined as the negative potential gradient. So when we are talking about E is equal to minus dV by dr, this is the potential difference. dV by dr is called potential gradient. How it varying according to the distance when we are taking. So from this, dr is minus dV by E, means the separation between any 2 equipotential surfaces inversely proportional to the electric field. So E is strong, dr will be small, means the separation between 2 equipotential surfaces are less distance than the E is strong. In the regions where the electric field is weaker, the separation between the 2 equipotential surfaces are far apart, and vice versa. 2 equipotential surfaces cannot intersect. So they cannot intersect. We will see you in the next video. Thank you for watching the video. Share, subscribe, like the video.